Hi, this is Yinhao Qian, and this is my lab demonstration for ECE 1110, project number 1, project demonstration. So, I have already listed the directions here. If you want to take a look, that's fine. And some additional information here is all the memories and register store value at falling edge instead of rising edge. And no stallings are present in the CPU because all the branch instruction can actually be resolved in the second instruction decode stage. So, also, add R0 is reserved for no operation, so no addition will be actually performed if this instruction is received. And lastly, the high clock frequency may result in a loss of values. Okay, so let's go to our first test case. We'll first set number 2 to all registers. And this can be done by giving some simple instructions like ADD-UI, R0, immediate 2, and then 2 will be fed into register 0. And we'll do the same thing for register 0 all the way to register 7. As we can see, number 2 has already been fed to all the registers. Okay, so let's run the actual instructions are given. So we're going to first add the number 11 to register number 2, which will give us 13 for register number 2. And then we're going to subtract register number 1 from register number 5 and store the value in register number 5. So 2 minus 2 here from register number 1 is also 2. So 2 minus 2 is 0. And we're going to add 5 to register 6. So 2 plus 5 is 7 for register 6. And then we're going to add the value from register 3 to register 4, which is 2 plus 2 equals 4. And then we're going to add 5 to register 1, which is 7. And then we are going to subtract register number 2 from register number 5. So register number 2 has the value of 13, and register number 5 has the value of 0. So 0 minus 13 will have the value of negative 13. And then we're going to put the value of R1, R2, R4, R6, and R5 in sequence. So R1 equals 7, and R2 equals 13. D is the hexadecimal format of 13. And R4 equals 4. R6 equals 7. And R5 equals negative 13. In 2's complement form, it's actually FFF3. That's for the first test case. Now, let's move on to the second test case. We're going to, again, load the binary file from our benchmark folder and then clear the buffer. It only has 5 instructions. However, there's a store word and load word instructions present in this test case, so we're going to be using the memory space. Okay. Just as for the test case 1, we're going to pre-assign values to registers. So it's 10, 15, 10, 4, etc. Okay, so it's 10 for register 1, 15 for register 2, 10 for register 3, 4 for register 4, 0 for register 5, and 4 for register 6, and all other registers equal to 0. First, we're going to store the value from register 3 to the memory address of register number 4. So register 3 has the value 10, and register 4 has the value 4. So we're going to store the value 10 into the memory position number 4. So we can go to our memory space and put 10 at position 4. As we can see, since the memory stores value in the memory stage, we can already see A has been stored in the position 4. And then we're going to add the value from register 1 and register 2. So it's 10 plus 15 equals 25 for register 1. And then we're going to add 10 to register 2, which is also 25. And then for the load word instruction, we're going to be fetching the value from memory at position stored in register 6, and store the value fetched to register number 5. So currently register number 6 holds a value of 4. So we're going to fetch the value from memory at at position number 4, which is equal to 10 as we just stored, and put 10 back to the register number 5. So it's actually here equals 10. And then the halt instruction is detected, and no more instruction will be fetched. That's for the test case number 2. And now let's move to the test case number 3. Again, we need to load the binary file into the instruction room. We'll first pre-assign registers into a pre-assigned value of 10. and then add 1. No, sorry. So it's add register 1 and register 2, which is 10 minus plus 10 from register 2 equals 20 for register 1. And then add register 1 and register 3. So currently register 1 has a value of 20, and register 3 has 10, so 10 plus 20 equals 30. As here, we can see, since R1 is just R1 has just updated value from the last instruction, the forwarding unit will be used. If forwarding unit is not working correctly, it will actually be adding 10 here. But if the forwarding unit is adding correctly, 20 will be added here, and the correct value will be 30. As we can see, the value did turn to 30. And now we're going to add register 2 to register 4. So it's 10 plus 10 equals 20. And then we're going to be subtracting register number 4 from register number 5. So register number 4 is 10, and register number 5 is also 10. And 10 minus 10 equals 0. Oh, sorry. It's actually 20 here. My bad. Since register number 4 is 20, it's actually 10 minus 20 equals negative 10. Since we just updated the value in register 4, the forwarding unit is used. If the forwarding unit is not used, it should fetch the value here, 10. But if the forwarding unit is working correctly, it should be minus in 20, which will yield the correct value of negative 10, which we can see here is correct, negative 10 for register 5. And then we're going to simply add 4 to register number 2, which will have 14 for register number 2. And then add 4 to register number 1 again, so which is going to be 20 plus 4 equals 24. And lastly, we're going to put the value from register 3 to the LED, which is 1E. And 1E is the hexadecimal format of 30. And then R5 is negative 10, and F6 is the hexadecimal 2's complement format for negative 10. So that's for the third test case. Now let's move to the fourth test case. We're going to assign 2 to all registers except for register 3 and register 1, which is equal to 1. Okay, so we have a problem here. The problem is the branch instruction here and here will have the relative instruction index here. It's 3 and 6. And 3, 6 is corresponding to 0, 1, 2, 3 here, and 4, 5, 6, 6 here. And because we have some more instructions for this case, we need to change the relative position for the instruction. And that's why if we go to our instruction ASM, we can see the relative number has been changed to 12 and 15, because 12 is corresponding to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which is ADDUI R44, which is corresponding to here ADDUI number register 44. And ADDI register 5, 7 is corresponding to 13, 14, 15 here, which is ADDI register 5, 7. And after the relative position has been resolved, we can continue running our instructions. We'll first add R2 into R1, which is 1 plus 2 equals 3 for R1. And then branch equals 0 for R3. So we're going to see if the value from register 3 is equal to 0 or not. And if it equals to 0, we're going to jump directly to the ADDUI instruction here and skipping the instruction here. However, if it is not, we will continue running this instruction and then this instruction. And if we look at our register value number 3, we can see the register 3 has the value of 1, which is not equal to 0, since the branch will not happen. So the next instruction should be ADDUI register 4, 4, which is adding 4 to register number 4, which is 6 for register 4. Oh, sorry. What was I thinking? Yeah, the second instruction will be executed. Since it will be executed, 2 will be added to register 2, which will have a 4 for register 2 here. That's why we have a 4 here. And 6 will corresponds to register 4, which is 6. Okay. And then we're going to move to the next branch instruction. And we're going to compare the register R1 if it is greater than 0, because the instruction here is BP instead of BZ. And we can see that the register 1 has a value of 3, which is indeed more than 0. Now the branch will happen. And if the branch happens, it will jump directly to 8 add immediate register 5, 7, skipping the value, skipping this instruction here, ADDI R6, 6. We can cross instruction here. And the next instruction will directly add 7 to register 5, which will give us 9 for register 5. And register 6 will remain the same value, which is 2. Okay, that's where the magic happens. And then we're going to put the value from register 2, which is 4, into the LED. And then register 1, which is 3. And then register 3, which is 1. And then lastly, register 6, which is 2. And then halt the instruction. So no more instruction will be fetched. And that's the demonstration for all of the 4 test cases provided from the canvas. And thanks for watching.